Okay, we continue with conductivity, okay, or conductor. So now frequency dependence of conductivity. We have last time seen reflection and EM waves, and good conductor, bad conductor depends on frequency, sigma by epsilon omega. Now I'm going to look at what is the possible frequency dependence of conductivity itself. And from there, we will actually go to frequency dependence of permittivity as well. Let's start. Uh, so, is conductivity of good conductors omega dependent? That's the question we're asking. And typically, this comes under the AC, alternating current conductivity of conductors. And I'm giving a very elementary treatment to be able to give a feel for just the simplest possible model. So let us consider the simplest model of the Drude metal that we have already done, okay, which means it is n free electrons per unit volume suffering random collisions in, let's say, tau c, collision time, tau c. This is what we had discussed while discussing Joule heating, for example. That's the simplest possible model of a metal. And let's continue with that. So the equation of motion under relaxation time approximation, as discussed earlier in connection with Hall effect and Joule heating, is dp by dt minus p by tau c minus e. Only force is this, but you are losing it every time there is a collision, and mean time for collision is tau c. Okay, that's something that we're already familiar with. Now let me subject it to a time-dependent electric field, such as ET. It could be a real, let's say, cos omega t, so real of E naught e to the power minus I omega t. Okay, so that's the simplest harmonic excitation that we can subject this equation of motion to. So we seek a steady state solution of the form that what is the P solution. So basically we're looking for what is the P naught, the amplitude of the momentum variation with omega. That's the frequency. So aim to get omega dependence of P naught. That's what I've just seen. So substituting this, what do? We substitute this Pt into the equation of motion here. And of course, since this is e to the power minus I omega t will cancel here. And only thing will remain is the, after differentiation from here, it will come minus I omega P naught omega. P naught itself is a frequency of omega. Here P naught minus P naught by omega by tau c, and of course minus E naught as a function of omega. All right. So and then, okay, so let's, but we know that J naught, okay, there's a current corresponding to P naught, is minus NE, the velocity. Velocity is P naught of omega as by M. M is the mass of the electron. So I can find out what is of J of T, the current density. J of T is a real part of J naught omega e to the power minus I omega t in steady state. Okay, so from P naught I've gotten J naught, so I know what is J naught, so I know what is the JT that is going to go. So J naught omega I can write down as NE P naught omega by M, and which is from here, okay, NE square E naught M 1 by tau C minus I omega. Okay, I just solve for P naught from here and plug this into my J naught omega. Okay, J naught, I'm just defining what is J naught, right? But J naught omega I obtained from P naught omega. So J naught omega is minus NE P naught. I solve from P naught, and this is NE square E M 1 by tau C minus I omega. And so I can write down this in terms of the amplitude, the current amplitude, as the conductivity, which is now frequency dependent, into E naught. Okay, so, and hence this is my AC conductivity. Sigma as a function of omega is sigma naught, where sigma naught is NE square tau C by M, as you had seen. This is a DC conductivity, not meaning DC. When there was no fluctuation, I have only applied a electric field. But now electric field is fluctuating. In that case, sigma is now become omega dependent, and that looks like a quantity which is imaginary, 1 minus I omega tau c. What does imaginary means? Doesn't mean that sigma is imaginary. It only means it has both cos and sine. Because if we drove it with only cos, then you also get a component which is 90-degree phase out of phase, which is sine omega t. Okay, that's all it means. You can always multiply 1 plus I omega tau c here and 1 plus I omega tau c here, and you will get two components. The imaginary component is 90-degree out of phase. So this is a DC conductivity, and AC conductivity is imaginary, which means out of phase component also can appear. So which means if the driving force is very large, then the electron cannot respond. Okay, since the response time is limited by in the gas by its collision time. Okay, so if the frequency is too fast and collisions are happening more rarely, then of course this model will not give you, so there's a lag. Okay, so if omega tau c is very small, omega into tau c very small, then imaginary part goes away, then of course we recover the DC conductivity, okay, for small omega. Or anytime omega tau c is much less than 1 by tau c, we get this. But if omega tau c is much larger than 1, then we get a purely imaginary sigma, okay, which means we start getting a out of phase oscillations, okay, and then it can be also reduced in its amplitude, because sigma, then it will be sigma naught divided by omega by tau c, and you are saying omega tau c is large. If omega is very high, then sigma is not conducting at all. So it stops being conducting even from this point of view, from conductivity. Okay, so for a high conductivity, the sigma can go to 0 for high omega, for high frequency. All right. So let's look at the physical significance. Okay, this is called the collisional regime. I will also look at the other regime. So we have figured out that sigma omega is sigma naught 1 minus 1. So what I have been saying in words, let me do it with pictures. Okay, so let's plot it. Let's plot how sigma as a function of omega will work. Normally we work with, I'm getting the magnitude, the imaginary is a complex quantity, so I am plotting the magnitude. Okay, and since omega can vary from almost DC to very high, instead of plotting with omega, I'm going to plot with log of omega. All right, such that we many orders of magnitude of omega is represented on the axis. Okay, then what I'll get is this. So for a very small omega, it is sigma naught. Okay, and then only when omega tc starts becoming important, okay, as compared to 1, this will go down. Okay, this will go down, and of course for very high omega it will go to 0. Okay, so so it will come down to almost half of this. Okay, around approximately 1 by tau c. Okay, factor of root 2 can be there. But so when log of omega is or omega corresponds to 1 by tau c, log of 1 by tau c, this will be nearly half. Okay, so which means if I know, if I can do such a measurement, then I can find out my tau c. All right, so this is AC conductivity. But what is the order of tau c? The collision time. This is of the order of 10 to the power minus 14 seconds, okay, or 10 to the minus 15 seconds, okay, and hence this will happen in how much hertz? 10 to the 14 to 10 to the 15 hertz, and that is light. So purely from electrical considerations, okay, from DC conductivity, we see that its conductivity will start coming down when the electric field is not from outside, but is the electric field that is of the EM waves, and especially in visible light. Okay, so I'll summarize those comments. So if omega is much less than 1 by tau c, then the conductivity is the DC sigma naught. I've already said that. 1 by tau c is of the order of 10 power 14 to 16 hertz. That is of electromagnetic wave frequency of the, in fact, around the visible. 10 power 15 hertz is around visible. So I have ignored the magnetic field. can be ignored since its effect is smaller by a factor of, let's say, V by C. C is light, and V is of the order of only 1 meter per second or so, the drift velocity that we had said, okay, even with a very large current. And hence, the factor ratio V by C is of the order of 10 to the minus 10, and hence in most of our treatment of the effect of EM waves interaction with solids, we ignore the magnetic field unless it is extremely high intensity and so on and so forth. All right. So that's one reason that we ignore magnetic field. But so typically then, what is this region? This region is UV. All right. So it stops becoming a conductor in the UV region. Okay. And I'll have more to say about this. So position dependence, I have also, you can see that I have just done a single oscillator problem, and but my wave is could be actually dependent on position. Okay, but position dependence, lambda is of the order of uh, 400 nanometers or 4,000 angstroms, whereas the collision time, the space over which collision occurs, is the mean free path time. That's typically 10 angstroms, 100 angstroms. So that there is a huge difference between 400 to 1,000 times difference. And hence, we can almost say that of the region over which these collisions are occurring, the field is within the time period that you are looking at, the field is nearly the same. Okay, it's a very rough model, but yet it has its value because I can justify these time scales. So let's go to, this was the collision region. But what about if the time is so short that it doesn't actually have time to go and collide? It's much, much smaller than tau c. So that is what I'm calling as the collision-less regime. Okay, so let's see. We can now consider the same thing. Let's consider again the simplest model with n free, but the time so short that it does not have an opportunity to collide, okay, with whatever it is colliding. Okay, that is what determines the. So it is basically just wiggling back and forth. Okay, and it doesn't collide. So in that regime, instead of conductivity, we can talk about the permittivity. Okay, because you can see conductivity is going down, and it is already is becoming more like an insulator and or a dielectric, and hence the same metal we can talk about what is epsilon omega. That's an interesting. So I'm doing both sides. Okay, where it is treating it as a conductor, and now going the collision regime where it has stopped being almost conductor. So then I can write down m dx square by dt is minus EE, that's the force, and there is no collision now. So I've dropped the collision term from the Drude model. Okay, and now I subject it to the time-dependent electric field of the wave, electromagnetic wave, let's say, and I do not worry about the space. I only worry about the time-dependent E naught e to power minus I omega t. So now we look for the omega dependence of this amplitude that is x. Okay, it is vibrating. This you have done in physics 102 a lot, okay, in oscillations and simple harmonic motion. This is basically simple harmonic motion. So we look for what is the omega dependence of this x naught. All right. So we plug it into the equation of motion to obtain that. This will give you twice. So minus omega square mx naught and minus e naught. I have cancelled the e minus I omega t, as we know, as we have been doing, and hence I know x naught now is a function of omega. Okay, so now the dipole moment of, if it is goes out from the mean free position, we know it's a dipole. So the dipole moment of such a electron would be minus ex naught. It's oscillating, but its amplitude is x naught. So now I can find out one electron's dipole moment. Okay, each electron is minus e, and it is displaced from its mean position by the amplitude x naught. And x naught I can already figure out it from here. My e naught by mx naught. So this e minus minus of course cancels. This minus retains there. So e square e naught by m omega square. So this is the, while it is oscillating with a certain amplitude, each electron corresponds to as if it is one free electron, as if it's a dipole, because from its mean position it is going out to x naught. All right. So the polarization then, if I know the dipole moment, then I can calculate the polarization. So polarization of the color of all electrons, not one electron, is now n electrons per unit volume. So minus n e x naught. Minus e x naught is the dipole moment, and there are n electrons per volume. So the total polarization for volume is just this, minus n square. So I know P. If I know P, then I can calculate the susceptibility. Susceptibility is chi P by epsilon naught E naught. Okay, and that is, so E naught cancels. So I got n square m uh, epsilon naught omega square. So I got the electric susceptibility for this uh, gas, okay, electron gas. So the relative permittivity then simply 1 plus chi e, and that is 1 minus n square m epsilon naught omega square. All right. So we have calculated the uh, relative permittivity of this gas, which is in the collisionless regime. There is no collision occurring. All right. So now let's look at, so I can write down this as 1 minus n square m epsilon naught omega square. Okay. So I can rewrite this. Okay. So this quantity n, m, and epsilon naught are all constants. N is for that metal. Okay. M is for free electron. Epsilon naught is epsilon naught vacuum, and hence E. So this only parameter is there, actually the electron, and hence I can collect n square by m epsilon naught and say that it is omega p square is that, and hence the relative permittivity is epsilon r equal to 1 minus omega p square by omega square. Omega p square is defined by here, and that seems to be a characteristic frequency for that material because it only depends on m, e square and m epsilon. So if I know the electron concentration of the metal or the conductor, I can find out what is the characteristic omega p. So that is a material dependent property, and my ER simply depends on 1 minus omega p square by. So I have figured out what is the omega dependence for this simple model, okay, so of the relative permittivity. Okay, that was our main aim was there. So now let's plot it. Okay, so ER, it can be, of course, 1. It is less than 1, and I'll plot it as a function of omega by omega p. Omega is my external field that I am applying. All right, and hence I will say that this is since omega p is the scale in the problem. So I will, instead of plotting as a function of omega, I'll plot omega for omega p. Then it will be true for any material with whatever omega p. And then this is the omega is equal to omega p point. How does it look like, this quantity? Okay, you can think about it and see that it will look like that. Okay, so now it's negative. Okay, uh, below, if omega is less than omega p, then it's of course, okay, negative. ER is negative. And we know the relative permittivity of typical dielectrics are positive, but electric ER of a conductor can be, uh, uh, you can think of it negative. So, which means ER negative, meaning, okay, refractive index is complex, okay, N is root over ER. Refractive index is complex, which means the electromagnetic wave is going to decay and is not going to travel. So, in this frequency regime, okay, that is omega less than 1, okay, the EM waves cannot travel, but omega larger than 1 omega, they can really propagate. All right, in that medium, and hence now this particular frequency is called omega or omega p, and so less than omega p, it is like a reflection that we had thought of. So like a conductor, and it will reflect depending on its conductivity, sigma by epsilon omega. That will determine how much of it is getting reflected. And if the frequency is more than omega p, then it is transparent, just like light is visible light is transparent to our window glass pane. Okay, so this material, which is a conductor, can be transparent to EM waves if that EM waves omega is greater than omega p. And why is this called P? This is called the plasma. Uh, okay, so I've shown that also with my hand, that it will decay as it go into in this regime, and but it is not a very good drawing, but it will keep traveling, and it will be transparent, just like light is transparent to glass. Even a metal will be transparent to waves or radiation, which is omega greater than omega p. All right. So this is called the plasma frequency. That is why I have been doing this uh, uh, subscript P, because this is called the plasma frequency for that particular conductor. Okay. Uh, so good conductors, okay, are so Drude model is a good model for good conductors. Okay, good boy conductors. So good conductors are transparent to EM waves, which are greater omega is greater than the plasma frequency omega p. All right. Okay, so now can we measure this plasma frequency? Do we know how do I measure? There are many experiments, but the simplest I can think of, in one region it is reflecting, in the other region it is letting it pass. So what do I measure experimentally? I can measure reflectivity. All right. So how do it look like? So simplest is measure reflectivity. Okay, as a function of frequency or wavelength. Okay, of the radiation. Typically in the lab, it is easy to measure wavelength, and hence and of course wavelength and frequency are related, and hence either you can measure as a function of frequency or as a function of wavelength. Good conductors, such as typically good conductors are what? Alkali metals like sodium, okay, are transparent to UV, that we have I have already been hinting from sigma measurement, and this omega greater than omega p is also is UV. So this is I just wrote it with my hand. So reflectivity. So if it is a very less omega, it's like a perfect metal almost. Okay, so everything is reflected, like almost like a good conductor is a very good conductor. So let me assume that it's almost like a perfect conductor. So for good, this also could be plotted with function of log omega to consider. So then it remains like a good conductor, and then omega starts decreasing. You know when? Okay, if omega starts becoming close to 1 by tau c, where tau c is the collision time, then it will start decreasing, and then it becomes zero. Okay, how well you can measure that zero experimentally is a but we can measure it well because we know that it goes to zero, and after that it's becoming transparent. So I can always measure this inflection point, that it was reflecting and now it is transparent. It is now letting it propagate. So this measurement is quite easily possible. What is the cutoff wavelength? Okay, which wavelength of this wavelength is omega is large, means wavelength is small. So which is the smallest, largest wavelength that it is allowing to transmit? And then we know the cutoff wavelength, and that is the measurement of the plasma frequency. Okay, and so this is like conductor like. This part is conductor like, and this part it is letting it go. So it is like dielectric like from this perspective also. So first I did sigma as a function of omega. Now I am doing epsilon as a function of omega and measuring reflectivity. Now you know reflectivity. If I do an experiment with normal incidence, then I can measure reflectivity. Just a detector. I know a detector can say how much is getting reflected, and then they can record the reflectivity. So, and how good is this model? Looks like a very simple model. Just simple harmonic motion I did, and then got my such an important physical quantity. Now, lambda p corresponding to omega p. These are good metals. Okay, these are alkali metals: lithium, sodium, potassium, rubidium, cesium, datite, protium. So if you calculate from a simple formula, except a little bit instead of epsilon naught, you can take epsilon for that material, or instead of m, you can take free electron mass. That's a little bit modified in the effective mass and so on. If you calculate it, then it turns out to be 155. And what is observed? Exactly that. Of course, as we go on, slight differences keep appearing, but it's an extremely good model, okay, which a pretty close match with uh, what is calculated and what is observed for good metals. Okay, and so this is an important physical observation from a very simple model. Okay, that most conductors are transparent to UV light. All right, and it has lot of uses. Okay, so let me show you another important. So in metals, I have to take different metals to do this. But if I take a semiconductor, which is also can behave like a metal if I dope it, and is an N-type indium antimonide, and 300 at 300 Kelvin, what is done is you dope it differently. It's per meter cube. Okay, the electron concentration. So I'm varying the electron concentration, and you know the plasma frequency depends only on the electron concentration. Omega p square is n e square by m epsilon naught. N is the only parameter. So here the experimenter varies the doping of this material, indium antimonide, all right, and looks at the reflectivity. And here it is, instead of omega, it is plotted as a function of wavelength. That is what it just choose to plot as a function of wavelengths. It is exactly reverse of that. So smaller wavelength, it is behaving like dielectric. Okay, but as the carrier concentration is changed, then omega or lambda p, okay, the position of plasma frequency also changes exactly as uh, predicted by this formula that we have just found. Remarkable. There are lots of complications in a material, but you can still exactly find out. In fact, if you know this, you can find out electron concentration. If you do this experiment, then there is one way of finding out electron concentration. Okay, so here it is. So for lambda, which is uh, less than the cutoff wavelength for UV, it behaves like a dielectric. Okay, and and all reflective like and reflects like a metal if it is very large lambda. Okay, and then there's a transition point here. Neat data. Okay, which proves this formula very much. Uh, this is actually from a very old data, 1957. Okay, data, but so it appears. So it is not only through reflectivity; it appears in many experiments. Okay, with wherever there is a your excitation interacts with the solid, and if it can exchanges energy, then you will see the effect of uh, plasma frequency. Since the frequency, okay, normally you can associate a packet of energy with it, like h cross omega, and you will see that the this particular frequency exchanges energy with beams going through the solid, or laser beams going through the solid at that particular energy, and hence we know. There are not many experiments in which you can measure plasma frequency, but this is the simplest in terms of what you know. All right. So uh, what is actually happens at plasma? Okay. In last class also, somebody asked me. We always worry about the what is the microscopic. Why is that the epsilon goes to epsilon relative 1 minus omega p square by omega square? So that omega is equal to omega p, epsilon r goes to 0. So what is the microscopic mental picture that one can have? Okay, so what I'm going to show you that it leads to a natural collective mode of oscillations. Okay, and that's one of the modes of the oscillations of the system, and there is a match. Okay, let me explain. So let's consider that a piece of conductor in which is neutral, in which that a positive ion background is there, and the free electron gas is also there. Okay, so on top, so there is you saw the positive ion background. On top, I am putting the gas and is neutral. All the metals, the conduction electrons are negative and the ions are positive. So the whole sample appears neutral. Okay, but the positive ions are fixed in their places. They can't move, except they can vibrate a little bit. Whereas the electrons are all over the place and they are moving. Okay, that is what the conception of the conductor there with us. So now, suppose it gets displaced, okay, the whole of the gas together gets displaced to one side. That is, now it exposes the ions here are now this portion is not no longer neutral, and this portion as if has all the electrons, okay, more. So this is like a almost like a capacitor. Okay, I have displaced the whole of the all of the electron gas simultaneously, all the electrons to one side by a small amount. Okay, that amount. So, and I have a positive surface charge here. And what is the surface charge density? This is not conductivity. This is surface charge density. Okay, so N E, okay, and X. This is positive. Okay, if X is the amount by which I have, let's say I put X my origin here, then X is the amount by which it is displaced. X is a small amount. Okay, and here I would have minus NEX because electrons are there. Okay, this is a simple mental model. Okay, and then what happens? This is positive surface charge, this is negative surface charge, this is neutral. So I have a electric field, okay, which is in this direction first. Okay, and that will pull the electrons back. So I'll have a restoring force. Okay, so there'll be a electric field in this direction, which will be a restoring force. And how much? So this is X and this is, so this amount is X and this amount is X. So what is the electric field that will be there? That is the sigma by epsilon naught. This plus and minus. And this electric field, which has been as a result after the displacement, will try to restore it. Okay, and this is classic SHM. Okay, because md square x by dt square is not minus EE, and E is my NEX epsilon naught, and is the charge. Let's concentrate, though it has happened to the whole electron, all electrons are independent, so I am looking at only one electron. All right. So and hence acceleration is proportional to x itself. This is classic simple harmonic motion. I can rewrite this d square x dt square minus, this minus is important because it's restoring force, and ne square by m epsilon naught x. Now do you recognize this quantity? Ne square by m epsilon naught? That's my omega p square. Okay, that we saw in that context in the last slide. Okay, and hence this looks like if this is the mode, then this mode can give us this mode of oscillation, as if the electrons are going back and forth, but it's not one electron, each electron is the whole electron gas getting X displaced and then getting restored back. So this is a very different kind of oscillation, and because of that I call it as collective mode of oscillations, because the whole gas is doing collective oscillations. And then the relative permittivity then goes as 1 minus, just we have so this is the kind of mechanism that I want to have in your mind, which is possible. So what has happened is epsilon r has gone to 0 at that point, and that is actually a theorem. You can say that whenever that happens, it supports longitudinal oscillations in the medium. In whichever medium, if the response function epsilon r is nothing but a response function, if that response function goes to 0, then the medium can support longitudinal oscillations. So this is like a longitudinal oscillation. All right. So there's a collective oscillating as a group, and that's why they are called plasma. So this could be is interacting with the electric field, and let's say my electric field is in x is polarized in x direction and it's traveling in this direction. All right, and that is how it starts interacting with this particular mode. It sets up that particular mode of oscillations. Okay, and but only happens at that particular omega. okay, because there is a resonance with ease the electric fields omega, and with this omega, if there resonates, and at that time plasma frequencies are generated, or the plasma oscillations are generated. And it happens in not only just metal, it happens even in free space where there are both electrons and ions. Ions are sluggish and electrons are a lot more faster, and happens between two cathode and anode. And there is a lot of uses of this plasma, for example. But what is a plasma anyway? A medium in which equal amount of positive and negative charges are there, not just metal, anything. Okay, and it happens in stars, it happens in wherever. Okay, and at least one type is mobile. In a metal, the fixed positive ions are in the background, and conduction electrons are mobile. But these plasma is sometimes called the fourth state of matter, because there are lots of instances where there are very highly ionized gases behave like plasma. There is ions and electrons. They collectively they are neutral, but electrons can move, and of course ions can move at a different speed. And so, and we have plasma as a discipline within physics. Okay, plasma physics. It's a very important discipline, and has many applications, including core of Earth, the stars. Many of the experiments use plasma as a experimental tool. Okay, so let me summarize a little bit. This might be a little bit more than what you can expect in your course, but now that I've said so many things, I can also generalize a little bit. So this is what our wave equation actually looked in terms of harmonic solution, right? So k square in this. So instead of this, I can also pose as if my permittivity is complex with omega with a k complex. Okay, and then I take my epsilon naught mu naught out and omega square. So k complex square can be written, and put my permittivity as a complex quantity, as a quantity which is a function of omega and the k. Okay, and then these are the cases. Okay, if you don't understand fully, but I have showed you something. So if omega r is positive and real, okay, then k is also real, this k, and transverse em waves propagate with the that we know c by n, okay, the velocity. If epsilon r is less than 0 and real, then k becomes imaginary, and em wave is damped with a skin depth kind of distance that we have seen. This case I have not done, but you can take it from me that ER, if it becomes infinity, which means if this function has a pole, as we say, okay, if there is somewhere it diverges and becomes as a complex quantity, so it can be a pole at the bottom, so it can go to infinity, which means there is a free oscillation of the medium even without a force. That means oscillating already. And the case that we saw, exactly at the plasma frequency, if ER is equal to 0, it supports longitudinal polarized waves of the medium. Okay, sorry. Uh, and if it is complex, then K is also complex, even at zeros and poles, and waves are damped. So all these cases are important if I look at this frequency. Okay, so this is generalized. Okay, I don't expect you to fully understand this, but I've given you so much so that I thought I'll summarize it this way. It's a lot more generalized. Uh, Now let me tell you that this plasma, which is called bulk plasma that I've shown you. Now, as I told you, this is omega p, so H cross omega p, so they're called plasmon. So just like electron, okay, you can, or electron is a particle, this is an energy particle, just like phonon or there's a vibration particle. This is also called a plasmon, okay, in modern physics. And we have a whole discipline now called plasmonics, okay, and there are lots of scientific, and there's a lot more increasing now. The scientific and technical uses has actually gone through the roof. I don't have time to describe it here, but for example, surface plasmons, what I have described you is in bulk, but these plasmons can have a similar effect on the surface of especially of nanostructures, okay, metal nanoparticle, silver or gold, and from there actually find out the size of um, the nanostructure. Surface plasmons, for example, I don't know whether earlier people knew the physics, but they certainly knew that if you make gold in nanoscale, then the size determines its color, and that is what's been used in for example, Notre Dame. I don't know if after this Notre Dame fire, how much of this still is there, but it is. This is one of the rose windows of the Notre Dame de Palace. Every color here is from gold particles only, and these are from the plasmons. Okay, because the plasmon energy is different depending on the size of the gold particle. So you can just by gold you can get all these colors. Okay, you can look up many of the this what is called a stained glass, but it is not stained glass. There is no color paint to paint this. These are actually stuck gold particles. And now there are tremendous amount of uses of this plasmonics in microwave frequencies. Actually, you can design a cloak, okay, such that your enemy or even a whole car can't be seen. Okay, so and these are because of plasma. I'm just trying to make you more curious. I'm not trying to explain. Okay, and then this has given rise to what is called artificial. You take a metal and make holes in it, or shape it in many ways, especially in microwave frequencies. These are now giving rise to whole new curious optical properties. For example, negative refractive index and things like that. Okay, I'm just trying to make you more interested in a new discipline which is having many uses, especially for electrical engineers, or even biologists. Okay, use this plasmonic structures. Uh, in plasmonic, these nanoparticle uses are there in many biology experiments. So in all disciplines, so it's a growing field. Okay, but I have just told you from plasma frequency, it can now give rise to a whole discipline called plasmonics. Next time, this is all about conductors. Now we'll put together everything and look up any material and try and see what are the simplest possible epsilon omega. And I'll stop here. Okay, thank you.